Lastly, we look at the hardware part of deep learning, the GPUs. GPUs, graphic processing units, started as was originally designed to process graphics, to render images, because it is well optimized, right, for the kind of operation that we do on images, matrices, and so on. Uh, Now, the key idea in the GPU is that it has many um, uh, computation units, many small, simple computation units that it can apply the same operation in parallel. Okay, massive number of those, and that's as opposed to the CPU that has a few powerful cores, and it is optimized for sophisticated sequential tasks. The GPU has many, many cores, each lightweight. They do the same thing in many cases, and that's the kind of operations that they are optimized for. Okay, now this has become critical or an enabler actually of deep learning. And it started with a research project, AlexNet, that showed how we can use this unit that is designed for graphics for image classification, right? The AlexNet approach, which is a seminal paper in the evolution of deep learning. Okay. Uh, how do we approach, how do we use the GPU? We do it through frameworks that basically manage the access to the GPU, like CUDA and OpenCL, and we're going to look at CUDA. Okay, so first let's see the hardware design of the GPU. That's how it looks like. We have the CPU, and the CPU is accompanied by one or more GPUs. Okay, and while the CPU has its few cores, its each with its cache, L1 cache, and shared cache between multiple cores and a connection to the RAM. The GPU is connected to the CPU through some high throughput channel, the PCI Express, for example, and takes requests, okay, from the CPU. Basically, we'll say that the CPU runs kernels, these many small computations on the GPU. Who runs these operations? Well, these are the many different ALUs here. This is an abstract picture. We'll get more detailed soon. Okay, but you'll see that these many uh, units are controlled by one central control and also have their shared cache. And there's also a cache that is shared by all of the GPU, and it has its direct connection to the main memory. That's the general idea. The GPU lives alongside the CPU. Multiple GPUs can serve the same CPU. On the GPU, we execute the small programs called the kernels, and the CPU is the one who launches them. Okay, we call the CPU the host. Okay, the host manages the control flow, data movement between the memory and the GPU memory, or the memory that is the space of the CPU versus the memory that is the space of the GPU. And it also does synchronization, for example, ensuring that the GPU computations all finish before we continue on, assuming that the operation succeeds. And as I said, they communicate over a high-speed interconnect. Okay, now looking slightly deeper into the GPU, it has what are called the streaming multiprocessors. Each multiprocessor consists of many small processors, streaming processors. Okay, so some designs can be, say, 108 multiprocessors, each having 64 processor. Okay, or a 128 on a 128. So you see, in the end of the day, you have many of these uh, micro or processors, these streaming processors. Okay, now the idea is that we have many threads running on these streaming processors, and these many threads run a single instruction or run the same instruction, but on different data items. We'll see how it looks like next. And these threads are grouped in what we call warps. Okay, warps that again execute this same instruction. Now, CUDA is the language, the library that NVIDIA provides for controlling the GPU, for performing tasks on the GPU. And it comes with not just the basic library, but also some abstractions on top of the library. For example, abstractions that are designed to do linear algebra, which is so important in deep learning. Okay. And when you look at the machine learning, deep learning framework, PyTorch, TensorFlow, JAX, they have their translation of the operations into CUDA. And actually, they provide you with a flag where you can say, okay, I'm using CUDA, I'm using a CPU. If you're using a CPU, then it translates into standard CPU operations. If you use CUDA, then all of the operations are using their internal predefined compilation into CUDA. Okay, so this is how it looks like. We have the high-level languages, and Python has the um, machine learning libraries like Torch, okay, and Torch accesses CUDA, or it may have also some intermediate libraries like NumPy uses Numba, which uses CUDA, and CUDA is the one operating against the GPU. Okay, so that's how we program on the GPU. Now, importantly, the GPU gives you an interface of a hierarchy of computation units. And this is very important because with this abstraction, we can map our computation or our algorithm into executions of these small units. So we have the threads that each runs our kernel. Threads are grouped into blocks, and multiple blocks constitute a grid. Okay, just remember these terms, and each block runs a multiple of the warps. Remember, warp is the processing or the streaming processing runs multiple warps on a single multiprocessor. Okay, so as I told you, a warp runs on a single SM, and a block maps into multiple warps, all on the single SM. Okay, now importantly, when we call in CUDA a kernel, it looks like that. It is an operation with the arguments, and this is basically defining what it is, the task that we need to apply. But it also has these BT inside this syntax, um, which basically says we're going to run this task, op args, on B blocks, each running T threads. So this operation, op BT args, basically says run op args on B times T threads. Okay? Now, how does it help us? Importantly, when we execute that whenever thread executes that, the thread knows its thread number. It knows which index of B, which index of T it is in. We'll see how. Okay, so CUDA gives you several instructions, and we're going to see some examples of CUDA code, but things like, managing memory, allocating, freeing space, copying from the CPU space to the GPU space, and vice versa, calling kernels, defining kernels with this global thing we'll see next, and synchronizing. For example, on a block, wait for the entire block to finish its computation, sync threads, or wait for the entire GPU to finish whatever tasks that it has. Okay, so here's an example of a very basic CUDA program where we basically add the two numbers. Let's start with the main procedure. So we define here two arrays, HA and HB, and we want to compute their sum and store it in HC. Okay, so we define these pointers and allocate them, or let them point to allocated memory for the GPU A, B, and C. Okay, now we copy into A from the host the CPU to the device. The device is the GPU. Okay, could a memory copy from host to the device. We copy into the A space what we have in HA, this guy. Okay, same for HB. Okay, so now we have A and B in the space of a CUDA. We have C allocated for CUDA, and we call this kernel add ABC. Now, add ABC is very simple. It just means uh, take A, take B, and copy into C. But we call it with these dimensions. Okay, one block each having n threads, which means in the end of the day, n threads. Okay, now what does it do? Well, basically, it launches 1 times n executions of this code, and a pointer to our A, B, and C. But what is special? Well, you can know which thread you're running. Int I equals thread index dot x. Now the thread knows which index it is assigned to, and it's going to add just the corresponding numbers. Okay, so basically we have n threads and kernels executing in parallel, computing the corresponding addition. Okay, now once we did that, we just copy the memory of C from the CUDA memory to the device, to the CPU host, and free the space. That's all. Very simple. So you see the importance of a CUDA basically giving you this abstraction, this access to the parallelized execution with an access to the address, to the, think of it as virtual address or physical address of the thread that the thread is assigned to. That's the idea. That's the secret. Okay, let's look at another example. We have two matrices NAB, 256 times 256 each, and we want to compute their product. Okay, now we're going to run a CUDA program that where basically every kernel, every execution will be matrix multiplication, is assigned one entry of the output. It is assigned a row number and a column of A, a column number of B, and it's going to compute the dot product of the row and column. That's it. And we're going to run 256 on 256 kernels in parallel to compute the product. how do we do that? Well, the main is very simple. We define 256 um, threads. Okay, we organize it in this block structure. Okay, so it's a 16 times 16 block and a grid of 16 times 16 um, blocks. Okay, so we have 256 grids, each having 256 blocks. Okay, and now with this defined, we just call the matmul with the corresponding grid and block basically address. So what is happening in matmul? So from the block index and also the block dimension, we are computing the corresponding row of the matrix. I'm not getting into exactly how we're computing that. You can think of it offline, but this is not the important thing. The important thing is that from this block index and block dimension, we can understand which row this execution is assigned to, which column of B it is assigned to, and that's it. Once we have the row and the column, and we got the A space, the B space, and the C space, we're just basically applying the dot product in a naive way, okay, summing up the products, the individual products, and copying to C this sum. Okay, so in the end of the day, we have 256 times 256. Each is assigned to one column, one of the 256 rows, and one of A and one of the 256 columns of B, computing the corresponding entry. Okay? Um, and that's it. That's the entire computation. Okay, so let me finish with some key takeaways from the fourth module. It was an introduction to deep learning. We talked about the way we define deep neural networks as a composition of units or common units. Importantly, these are differentiable, function differentiable on their parameters. We talked about the fact that when we build networks, we use common composite networks as our building blocks, okay, for the bigger networks. We talked about transformers that build on attention, that itself builds on some other feed forward and so on. And we understood, or we made a big attempt to understand the intuition around attention. Okay, basically the idea that we have an observer that applies a query to context items. The query is run against the keys of the context items, and based on the combination of the query on the key, we get a weighted average over the collection of values of the context items. Okay, we talked about how we apply learning through backpropagation using the compositional structure of deep learning networks, naturally by applying the chain rule. Okay, and this gives us the gradients that we use in gradient descent, stochastic gradient descent, Adam optimizer, and so on. Okay, so this is a very important component, and this complements or is complemented with the corresponding hardware. Okay, the GPU. We talked about the GPU, what it brings us, why it is special, why it is different from a CPU, and how do machine learning libraries access the GPU or basically program algorithms that operate over the GPU, having defining a structure of blocks and grids and having the kernels accessing the indices. Okay, that gives you basically a picture of deep learning end to end. So we're done with this module. Thank you very much.